All right, in this video, I want to start talking about antiderivatives, which was section 4.8 in your book. This is the second video on antiderivatives. In the first video, the last video, we really just learned how to talk about antiderivatives, what the proper notation is to denote antiderivatives. So for example, this little mathematical equation here. That made no sense when you started watching the last video, but maybe now it does. This is saying if you take the antiderivative of this function, 3x squared, what you get for your answer is x cubed plus c. This family of functions is called the general antiderivative for this specific function here. That idea can also be denoted with a pair of statements like we saw here in green and like we saw here in red. What we did not talk about in the last video is how you would come up with this x cubed plus c. Now, all we did in the last video is we were like, well, the derivative of this is 3x squared, right? And you're like, yeah. Well, therefore, the antiderivative of this must be x cubed plus c. And I guess that's a convincing argument, but it doesn't explain to the student how you come up with the x cubed plus c in the first place. We don't just want to be able to check answers, we want to be able to come up with answers. In order to come up with that specific answer, what we're going to need is a new power rule. The old power rule, something you saw a lot of in Calculus 1, said that the derivative of x to the n power with respect to x is nx to the n minus 1 power. Maybe a little bit more informally, when you have x raised up to some number, all you got to do is take that number and bring it down in front of the x. But then don't forget to subtract 1 from that number and make that your new exponent. So kind of picture this with 3's in place of n's. This is saying the derivative of x to the third power is 3x to the second power. That was your old power rule. And it's sufficient for at least checking answers or coming up with the easiest of answers, like maybe the one example we saw in the last video. But what if I started you out with a new example here? What if I asked you this question? A question which could also be worded this way, where you specify that your function is 4x to the fifth power, and you're asked to determine the antiderivative of that function. You're like, oh, that's not too bad. This would just be x to the fourth power. No, wait. X to the sixth power. No, wait, that doesn't work either. Shoot, you made this all hard on me, huh? This isn't as easy as it was in the last one. I don't think it's obvious at all what the antiderivative of 4x to the fifth power is. Might be a good time to pause and think about whether you can come up with that answer. Can you come up with a function, or better yet, a family of functions, so that when you take the derivative of that family of functions, you get as your answer 4x to the fifth power? If you did everything perfectly, maybe you came up with 2/3 x to the sixth power plus c. And I don't expect you to be able to come up with that because I haven't taught you the new power rule, but at a minimum, you could check this answer, right? Think about how you could check this answer. If you took the derivative of this, constant goes away, the 6 comes down in front, 6 times 2/3 is 4, and then you subtract 1 from the exponent, you get 4x to the fifth power. Yeah, it looks like it checks out, but I'd still like to know a new power rule. Well, here it is. This new power rule is for Calc 2. Why is it for Calc 2? Well, because unlike this power rule for Calc 1 that deals with derivatives, this power rule for Calc 2 deals with antiderivatives. What this power rule is telling you is the antiderivative of x raised up to the n power. And unlike the old power rule, it's a little bit ugly. I mean, I guess this is a little bit ugly, but to me, this is even uglier than this is. It involves fractions for one thing, which generally students don't like a whole lot. But I guess the first thing I can do is convince you that it works. Since all we know about antiderivatives right now is that they're the kind of opposite of derivatives, I suppose we could take this answer and take the derivative of this answer and make sure it gets back to x to the n power. Well, because it's a sum of two terms, you take the derivative of each term individually. The derivative of the constant here would just be 0, so that would go away. And then when you're taking the derivative of this term, you'd use the power rule. You'd take the exponent down in front. So you'd have an n plus 1 times 1 over n plus 1. So those would cancel each other out. And then you'd subtract 1 from the exponent. 1 less than n plus 1 is just n. You'd be left with just x to the n power. Guess the power rule really does work. So, quick calculus break. You remember that day over the summer when we had the crazy fires near Ashland and there was all the evacuations going on and stuff? Well, today is that day. I'm making that video today. And there's some friends over here that got evacuated and things are just crazy and dogs are barking all over the place. So I've paused this video like 15 times while I've been making it, and I'll just edit that out later. But if it's a little disjointed, like if I talk about something and then it switches a little bit and it doesn't quite, I'm trying my best, I guess is what I'm saying. But hopefully I can edit this in such a way that the whole thing makes sense. I think where I left off is I made the argument for this new power rule. And maybe we can use that in conjunction with two other new facts that are kind of related to the power rule, but they're not exactly the power rule, to come up with this answer from this question. So here are those other two facts. These are the technical statements of these two more Calc 2 facts. And if this makes sense to you, great, you can just take this and kind of run with it. But I think it might make more sense if I kind of show you the Calc 1 analog of each of these guys. And you're like, oh, that's all you're saying? This is super easy. Two of the first things you learn about derivatives in Calc 1 that you start to take for granted after the class went on for long is that if you have constants out in front of functions, you can just ignore them for the sake of derivatives. If I ask you what's the derivative of 10 times x squared, well, don't worry about that 10. Just take the derivative of x squared, 2x, and then at the very end, multiply in that 10. You can pull the constants out in front of the derivative symbol, is what this first statement is saying. And the second statement is if you have a sum of things, like if I ask you what's the derivative of x to the 10th power plus e to the x, well, all you have to do is take the derivative of the x to the 10th power part, and then add to that the derivative of the e to the x power part. The derivative of a sum is just the sum of the derivatives. Right? Those are two really, really useful facts in Calc 1, and it turns out that the same thing, or damn near the same thing, holds true in Calc 2. That if you're taking the antiderivative of a constant times a function, if you're taking the antiderivative of, 10 times x to the third power, you just pull that 10 out in front and multiply that by the antiderivative of, what did I say, x to the third power? Whatever I said. Same idea down here. What if I ask you what's the antiderivative of x to the 10th power plus x to the 9th power? Well, there's nothing crazy going on there. You just break that up into two separate problems. You figure out the antiderivative of x to the 10th power, and then you figure out the antiderivative of x to the 9th power. With these three rules, I think we'll be able to do everything that we need for this video. And so let me start with this first question I asked you. I claimed that the antiderivative of 4x to the 5th is 2/3 x to the 6th power plus c. And I told you could check that using your Calc 1 knowledge, but what I want to show you now is how you could solve that using just Calc 2 knowledge, not Calc 1 knowledge. Pretend somebody started you out right here. If they said, let f of x equals 4x to the 5th, and asked you to determine capital F of x, the first thing you would need from the previous video is to understand what's being asked. Essentially, what's being asked is for you to take the antiderivative of 4x to the 5th power, which is written just like this. And to keep track of your work, what you could say is this is equal to, well, this is a constant times x to the 5th, so I could take that constant out in front of the integral. I could figure out the antiderivative of x to the 5th power, and then once I have that antiderivative, just multiply that answer times 4, just like you did when you were taking derivatives. How do I figure out the antiderivative of x to the 5th power? Well, all I have to do is use this power rule right here. All right, oh man, this is hard. What's going on here? The n is a 5, I guess, in this case. So 5 plus 1 is 6. I guess I would say this is 1/6 times x to the 6th power plus c. And this is the correct answer. You could simplify this answer. 4 times 1/6 is the same as 4/6, which you typically reduce that fraction and call it 2/3. And so I don't know, maybe this is a prettier answer than this, but either one is the correct answer. When you're done with the integrals, you figured out the antiderivative. In other words, if f of x is 4x to the 5th, capital F of x is 2/3 x to the 6th power plus c, just like we saw above here. For what it's worth, you don't have to do them in this order, but if you're wondering how I, your teacher, deal with these, I don't really have this memorized. I'm not like, okay, I have this formula, and now in this formula, playing the role of the n is the 5, so, and then plug this all in kind of in my head. What I instead do is, if I'm asked to figure out the antiderivative of, I don't know, pick what doesn't matter, x to the 11th power, for example. What I do, the steps that I do this in, is I start by writing the x, and then I deal with the exponent. So I add 1 to this exponent to make it x to the 12th, but then I remember that I'm not done. I have to bring a 1/12 down in front, because if I were taking derivatives, that 12 would have gone down in front, and I need to get rid of that 12. So you don't have to do them in that order, but for me, that just kind of makes the most sense. If that helps you, great. If it doesn't, you can totally ignore it. Here's a slightly different example. When you first look at this example, you might think that I messed up, which is certainly possible, although I don't think I did in this case. You'll note that I gave you the derivative of a function, f prime of x, and I asked you for the antiderivative of that function. That's 2 levels away. What do I mean by 2 levels away? Remember from the previous video, right? Capital F of x is the antiderivative of little f of x. Little f of x is the antiderivative of f prime of x. Right, so we're 2 layers away. I'm giving you this, and I'm asking you about this. We'll have to figure out the antiderivative 2 different times. But it turns out that's not so bad, because if you can do it once and get your answer, then there's no reason you can't do it again. So let's do it. A logical place to start is, well, if I have f prime of x, I can't get directly to capital F of x, but maybe I could figure out little f of x, right? Because little f of x is just the antiderivative of f prime of x. So maybe this is a good first step. You can write these up in any way that you want, but it might help to start using correct notation at some point so you can sort of keep track of your steps. I think I mentioned this in a previous video, that sometimes you see parentheses around here because the dx, which is really just a symbol that's tied to this integral sign for now that you can totally ignore, really applies to this whole thing. And as far as order of operations and stuff, it might look like it just applies to the 7 right now if you think about this as multiplication somehow. At any rate, sometimes you'll see parentheses around this 2x plus 7. I'm not going to worry about it right here. If I have to take the antiderivative of 2x plus 7, what I could do, and eventually you won't need to show all these steps, is first recognize that you're taking the antiderivative of a sum of two different terms. Right? So what you can do is just take the antiderivative of the first term and then add to that the antiderivative of the second term. So take this one problem and break it up into two different problems. And then one of these, you have this constant out in front, so we can pull the constant out in front of the integral. And now if we can just figure out these two antiderivatives, we'll be done with this thing. Well, the first one, they're both a little bit tricky, I suppose. This first one, you can think about this x as x to the 1 power. Right? So the first thing I'm going to do, if you do these the order that I do these in, is I'm going to add 1 to that exponent. So it used to be to the 1 power, now it's to the 2 power. But then I remember I'm not done, because if I were to take the derivative of x squared, I'd bring the 2 down in front. So what I get is 2 times 1/2 times x squared. This one, okay, what you are going to do, what 100% of calculus students do, is they recognize when they just have a constant here, they can just tack on an x. It's 7x. Oh, sure, that makes sense. If I took the derivative of 7x, my answer would just be 7. So it stands to reason that if I took the antiderivative of 7, my answer would be 7x. That's true. Technically, you can get there using the power rule if you want. If you think about this as 7x to the 0 power, well, I got to add 1 to that 0 power, so I get x to the first power, which is here. But then I'm not done. I have to do 1 divided by that power, 1. So 1 divided by 1 is just 1. It doesn't affect anything. You can use this new power rule to get from here to here, but nobody does. What people do instead is just memorize that the antiderivative of a constant is just that constant times x. Then don't forget to tack on the plus c. To be perfectly honest, not the end of the world if you don't, but it's a good idea to. What we figured out is that the antiderivative of 2x plus 7 is x squared plus 7x plus c. And you're like, okay, cool, so that's the answer to the question, huh? No, that was f of x, because that's the antiderivative of f prime of x, so that's f of x. So I get f of x is x squared plus 7x plus c. And actually, I can do better than that, because in the problem, it specifies that f of 1 is equal to 10. Right, so that means that 10 must be equal to 1 squared plus 7 times 1 plus c. Well, 1 squared is 1, 7 times 1 is 7, so I got 10 equals 8 plus c. Looks like c is just 2. So what my function f of x is actually equal to would be x squared plus 7x plus 2. And you're like, okay, you almost got me there, but I got you. That's my final answer, x squared plus 7x plus 2. No, because it didn't say find little f of x. It said find capital F of x. So we're not done. We got to do that whole thing again. Maybe we come over here. We say we want the antiderivative of x squared plus 7x plus 2. If you're really good, you might be able to jump from this to the final answer. Eventually, you'll be able to, but I'm going to show it in the different steps just because for those that this doesn't come quite as naturally for, I want you to have an algorithm for solving these. And I think that even if it does come naturally, it might not be a bad idea to follow the algorithm early on, because you'll see when these get to be a little bit more complex, it's nice to have something to fall back on. So what you could do is, based on this rule, I could split this up into 3 different antiderivatives, and that would look like this. And then I can pull this constant of 7 out in front of this integral here to get me to this line. Most people jump straight from this line to this line. They both split this apart and pull the constants out in front all at once. And if you're comfortable doing that, I would encourage you to do so. Save yourself 1 line of writing. The other thing that I want to point out is this little dx thing gets forgotten all the time. Later on, it'll be nice to have this here. You'll want to have this to keep track of your variable of integration. This won't just be a symbol. This will actually be something with meaning later on. So it's a good idea to write it all 3 times here, here, and here. It's a good idea to keep track of it throughout your process. But I can tell you from experience that a lot of students don't and they forget to. It's not the end of the world, but trust me, it'll make your life easier when things get harder if you're really meticulous in doing all of these different steps. Now we move on and we use our power rule. The antiderivative of x squared, the order that I would do this in is first I add 1 to the exponent, and then I remember that I'm not done. I have to multiply by 1/3. Don't have to do it in that order. That's just how I do it. For this next term, I'll leave the 7 alone, and then I'll think about this as x to the 1 power. If this is x to the 1 power, the first thing I would do is I would add 1 to that exponent to make it x to the 2 power, but then I wouldn't be done. I'd multiply this by 1/2. And then for this last term here, again, you could think about this as 2x to the 0 power if you really want to use the power rule, but most people don't. Most people just tack on the variable x in this case. And then don't forget to put on a constant. Most people use capital C for a constant. However, that kind of implies that we have the same constant over here as we have over here, which is not the case. So if you're doing 2 layers of this, it might not be a bad idea to change the letter that represents your constant, maybe D or something. Not a huge deal if you don't do that. You can simplify this a little bit. It's 1/3 x to the 3rd power plus 7/2 x squared plus 2x plus d. Another thing that I haven't said yet is that 99% of students at this point are way better with derivatives than antiderivatives. So a nice thing about antiderivatives, they have this built-in check. Right? If you're not sure if you did this right, just take the derivative. Right? You're good with that. You spent a whole term learning derivatives. Take the derivative of this. Make sure it gets you back to x squared plus 7x plus 2. If it does, you're in good shape. So this is my final answer. No, but damn near. Right? We still have to use the fact that capital F of 0 equals 5. So if I change all the x's into zeros, I should get 5 my answer. But if I change all the x's into zeros, this goes away, and this goes away, and I'm left with just d. Therefore, d must be equal to 5. And so my final answer, capital F of x, is 1/3 x cubed plus 7/2 x squared plus 2x plus 5. I planned on doing another example, but I filled this page up pretty good. And I want to keep these videos a little on the short side. So maybe we call that good. Maybe we stop this one here. I can regroup, check in with my friends that are evacuated from their home, and make a new video when life's a little bit more normal.